So, I'm pretty honored to be the first talker today. My talk is like I hope it's the most theoretical one, so things don't get boring if things are more theoretical than this one. So let's start with a short introduction of myself. This doesn't, does this have to be turned on too? No. Well, who am I? I'm an all-purpose SDR nut, and I was kind of involved with the GNU Radio project, maybe one can tell, and I hung out too much on certain mailing lists, so I got hired to do technical support for Ettus in the end, and those are the guys that produce the USRP series of SDR devices. This is a B210, a dual channel 56 megahertz bandwidth receiver. And so they pay for my stay here, and I'm kind of representing them, but only kind of, because I'm also representing the radio, and I'm also representing the whole science of software-defined radio and DSP here. So let me give you a short overview of what I'm going to be talking about. So I'm going to talk about what we expect from an SDR to be as a system. Then I'm going to go back a step and say, okay, we are after signals. We want to look at signals. We want to send and receive signals. So let's talk about what signals actually are and how to consider them in time and frequency domain. I think this is, hopefully this comes in kind of handy for the flex radio guys and for the direct Fourier. We'll see. Then I'm going to that's where we're going to make a break. And the second half of my talk will be after the lunch break, I guess. So I can have a little more time to go into detail with the examples. That's kind of nice to have. So let's start. So this is our prototype SDR device, right? We have some kind of antenna front end, obviously. We want to have some PA on the TX. We want to have some LNA on the RX side. That's pretty obvious. Then we have some analog front end, and I'm going to talk about that soon enough, but only shortly. Then we have some analog to digital converter and some digital to analog converter to make things work with actual digital hardware. And then we have software. Well, and software, this is where the magic happens, actually. Like, this is what makes SDR great, right? We have software that does all the radio stuff. So this is magic. Or thanks to Arthur C. Clarke, we know that that's only sufficiently advanced technology, right? And that being technology, we can actually pin down which kind of technology it is. This is digital signal. Oh, now this works. That's great. Just works the other way around. We can actually say this is digital signal processing. And I'm going to define that later on, and I hope this is going to be fun. So let's first talk about signals. Well, we know signals. Signals can be anything, basically. Anything that changes over time or over some other dimension. For example, the radio wave is a signal because it's changing of electrical field strength, magnetic field strength over time and over distance. Or a picture is a signal too, right? It's a change of color and intensity over X and Y. So for every signal, we know that if that signal fulfills certain criteria that, well, I have 30 minutes, I'm not going to talk about all of that, but basically for all interesting signals, Fourier says we can actually decompose that signal and represent it as a sum or an integral over a lot of harmonics. It's not said that these are a finite amount of harmonics, but it's said that it's definitely representable to an arbitrary amount of precision if we have enough harmonics. So, and as a bonus, if we know that the signal is periodic, which for example a continuous wave is, we know that the spectrum, so the actual frequencies and their coefficients that the signal is made of, is only discrete, which means it's not defined everywhere, but it's mostly zero, but there's a few points that it's not. So that's a handy feature. So let's look at a simple example. Let's look at a square wave, right? So we have in blue the square wave, and I'm gonna need to focus a bit more here. We have the square wave, and it's a pretty standard square wave. I've made it to be antisymmetric around time 0. And so I said, okay, if Fourier's is right, then I have to be able to approximate this with a harmonic oscillation. So this is my first attempt. This is a single sign, and doesn't do a really bad job at approximating the square wave, but it's not quite a square wave, right? So we only have the sine of the same frequency as the square wave. Now, the frequency of the square wave is obviously from -1 to 1 is 1 period, right? After that, it repeats. So the frequency is 2 because the distance is 1/2 because the period is 2. So if my first sign doesn't work, let's add another sign. We know that at the points where the original square wave was 0, our next square wave, our next sign should probably be 0 too, because otherwise we just add values where we don't want to have values. So I went ahead and said, okay, let's try the third 3 times that frequency. And this led, and then I added up the green and the red curve and ended up with the new green line. So this is interesting. So we're getting closer, right? So we're adding another harmonic. Now this is the 5th, and the 7th, and the 9th, 11, 13, 15, and so on. And now this is if we add everything, like the 1st, 3rd, and so on, until the 65th. So this is pretty square, right? And we can do this 2001, and yeah, basically gets indistinguishable from magic or the right signal, or whatever that is. What we just saw is that we can actually take the square wave and say, okay, there's discrete signs in there, and we know that from intuition, like if we have a spectrum that consists of a single tone, it's going to be a single line, like this one. This is a line, right? This is a single sign, and we have a lot of them. So I know that there was one at 1, there was one at 3, 5, 7, and so on. And this is actually what happens. This is like the magnitude spectrum of a square wave, and it goes on forever, right? We saw that. Even with the 1001st, there was still some contribution to getting it closer to the actual square wave. So this goes on forever. Why is that important? Okay, the Fourier transform actually exactly does that. It's a way to mathematically describe the signal in frequency domain, or take the frequency domain representation and get back the original time signal. It does a bit more than giving us just the absolute value of the spectrum, but that's a bit much math for today, and it's early, and we're not going to do that because it's boring. So again, this is the square wave, or an excerpt of the square wave, of course, goes on forever on both sides. And this is an excerpt of the spectrum, right? So, and why is this important? Well, spectra are important because everything in the real world affects the way things propagate, signals reach their target. And essentially, most physical systems are low-pass systems by some means, because, well, your wire can maybe transfer 50 hertz just as good as it can transfer 100 kilohertz, but it's not going to transfer 5 gigahertz just as well. So most systems have low-pass behavior, and that means that we can't have all the signs that we need to actually make the perfect square wave, right? So if we take the original square wave spectrum and have a low-pass behavior, so our filter sets all the signs bigger than 7 to 0, right? Then we will have our square wave, but it will just look like this. It's not the original square wave anymore, right? So this is why bandwidth is important to signal integrity. You can't have a very straight square wave or anything that has a very sharp edge within limited bandwidth. So this is why most people that will present their SDR devices will put an eye on how much bandwidth they can actually achieve with that, because that limits how fast you can observe changes in the spectrum or in the signal actually. Right, signal, time to my signal. So let me have a look at the time. Okay, I'm gonna put some more in here. So remember this slide, right? We want to talk about digital signal processing in the end today, because we want to do software-defined radio and not talk about only signals. So what is digital signal processing? Well, first of all, digital signal processing is processing of signals. So we're working with signals, but instead of taking like the actual voltage or the actual field strength or the actual current or temperature or whatever, we first convert them to digital signals. And then we do that, we deal with that in software or in digital hardware, which kind of is hard to tell apart if you're talking about FPGAs and similar devices. So what is a digital signal? Well, a digital signal is just a signal, so something changing over time, for example, but it only takes discrete value. It can't have the value of pi if pi is not a the valid value in your digitization. So, and it only exists for discrete times. So it won't exist between two sampling points. By the way, I've got enough time that, so if I say something wrong or you don't understand something, please raise a hand and give me a short question. So let's look at this. This might be an analog signal, right? This looks like a sine wave, and we have some noise on here, and it takes pretty much any value, right? And because we're not band limiting it significantly, this noise can have very, very high bandwidth, basically be wide. So what we're going to do now is we define some sample times. This is what I try to hint at by adding this grid. And we define some valid values, which is why I have the horizontal lines here. And then we go ahead and say, okay, let's take an analog to digital converter and just look at these times and determine the value of the signal at that point. So this is what happens. We get the signal and we look at exactly that instant. In practice, it's not really the instant. There's something that, again, integrates. But in theory, just look at that time. Discrete point in time, and we end up with a series of samples, right? This is a number, this is a number, this is a number, and this is a number. And so we can still see the original sign in here, right? But it's not the same signal anymore. It's a digital signal representing the analog one, more or less well. And as I said, one of the major features of that is the fact that it can be represented as a series of numbers. So instead of our series of points, we just get the series of values. Which is nice because series of values and numbers, well, it's actually what computers can handle. So yeah, that makes it easier to process than just having voltages. So let me go back to the concept of sampling. So we say, let's take away the noise and just look at the sine wave, or actually this is a cosine wave. So this was the analog signal, and I added the sampling times as vertical bars here, and marked around the points, and so we get our samples. And now we want to reconstruct the original signal, right? And this is kind of obvious, right? With these points, there's like only one solution, obviously, to get the original signal. This is reproducing it by drawing a line straight to here. Easy. There's more than one line that actually explains all these points, right? So what we're seeing here is that not only our original cosine represents this, produces these samples at these sample times, but also another signal which has 7 times that frequency does that, and we can play that game with other frequencies too. So this is really bad because suddenly we have samples, but they don't mean anything anymore because we don't know if it's like the cosine of pi x or it's the cosine of 13 pi x or 19 pi x. So what are we going to do about that? So there's always going to be ambiguity if you sample a signal if you don't know what the original frequency of that signal was. It can be at frequency f, like the lowest frequency explanation of something, or f plus f sample, 2f sample, or in fact any multiple of the sampling frequency above that what would explain that at a minimum frequency. So this is an inherent feature of digital signals. Their spectra are not clear without further information. Yeah? So we can only say, okay, if we look at this bandwidth of f sample, okay, I can. So if we look at this bandwidth of f sample, we know that the signal in there can only be this and this, consist of this and that harmonics, but we can't say that if we consider all the possible f sample bandwidth, we can't say in which we actually are. So our spectrum repeats every f sample. So thanks. Yeah, great, thanks. So the fact that our one cosine pi 1x ends up at the same frequency as our cosine 7x is called aliasing. It's basically the fact that the spectrum is periodic leads to all the signals that have a frequency plus a multiple of the sampling rate ending up at the same place. So if we want to avoid that, because we want to have clarity and not have all the noise at all the frequency and all the interference in our digital signal, we gotta have some anti-aliasing filter first. So, and that's why every sampling device has a filter in front of it. Otherwise, it will totally be useless because noise has pretty much infinite bandwidth, and you'll end up collecting all the noise, all the interference from other frequencies. So, and the nice thing, mathematically, it works the other way around too. It's not quite the same mechanism, but basically, if you just convert something digital to analog, you also have to make sure that you don't end up with images. So that's why we have what we call reconstruction filters after every DAC. So I have 5 minutes left. So we can actually use that aliasing, yeah, to our own gains. We can just care for the lowest frequency thing, so we don't have everything that we see actually ends up at the same frequency that we are interpreting at. Or we can have like, okay, we have a sampling rate of, let's say, 10 megahertz. We're seeing something, we want to see something at 21 megahertz. So we just filter out everything below 20 megahertz, and our 21 megahertz frequency would end up at 21 minus 2 times 10, so at 1 megahertz. This is really nice. So because with this technique called undersampling, we can analyze signals that are faster than our ADC actually works. So I think this might be a topic for the flex radio guys. This is really handy when digitizing signals that aren't extremely high frequency. Because you don't have to have a mixer, you don't incur some noise in the mixer, you don't incur frequency offsets and stuff. But it's kind of hard to do if you're going into the gigahertzes, because you have to have filters that filter out everything below. So my respect to everyone who buys and builds a filter to filter out everything below 5 gigahertz, to have a 5 gigahertz direct sampling receiver. Most of the time, you don't want to do that, because if you can have a device that can flexibly tune, you would need adjustable filters, right? You need different filter banks or filters that you can tune. And that's going to be hard to build and expensive. So you typically, for high frequency, go the mixing way and convert your signal to lower frequencies simply by multiplying it with a sine. But that's a different story. So I think I'm going to make a cut here. Are there any questions so far? I have 3 minutes if the next speaker could already. So.
The maximum frequency which you can sample, in trying to reconstruct an alien signal, is that also limited by the sample hold time of your ADC?
Sorry?
The sample hold time of ADC, is that limiting the...
Yeah, of course. Like, the question was, when you're looking at a practical ADC, then an ADC always has a sample and hold sub-device, I call it, like, which takes the analog signal, observes it, then holds that value typically by charging a capacitor, and then digitizes that value, because you can't observe something that moves very fast just in time. You often need to do multiple steps with the same value, so you need to sample it at one time and hold it for a certain amount of time. So of course the sample and hold time of an ADC is kind of a low-pass filter. Not only kind of, it is a low-pass filter, because you charge a capacitor usually, and that's inherently an RC low-pass filter. So yes, that puts a natural limit on something. Yeah. So.
Any further questions? You have another chance of asking your questions after the lunch break, where Marcus is going to take over another slot.
Thanks.
Yeah, I must thank you. That's really fantastic.
I'm totally surprised I'm allowed to do that. Like,
yes, well. Okay, then a big applause to Marcus. Thanks very much.